Swayam Prabha. Digital India. Educated India.
So, I have a couple of answers. One of the answers is when there is no resistor. Now, that is not correct actually. The correct answer is, see, why do we get two different solutions? Let me expand this. What this means is, when I have this plus and minus, one of the solutions P1 is minus R by 2L minus half square root of R by L square minus 4 by LC, and the second solution is minus R by 2L plus half square root of R by L whole square plus minus 4 by LC. Now, when will these two be equal to each other? Obviously, if this term you have a minus sign here and plus sign here. So, obviously, they will be different from each other unless this entire thing happens to be 0. The term under the square root happens to be 0. Okay. So, if this part is 0, that is R by L square is 4 by LC. You can simplify this. I think that is the answer that was given by Suganya, but I will leave it like this. Under this condition, you will have two identical roots. Okay. Now, if this quantity under the square root is positive, then it will have a real square root, right. If this is positive, it will have a real square root, and the two solutions P1 and P2 will be real and different from each other. If the quantity inside the square root is negative, then the square root will consist of an imaginary number. Okay. Then this P1 and P2 will be complex numbers and they will be complex conjugates of each other. Is this part clear? Please let me know. In summary, there are two solutions to P, P1 and 2, which are minus R by 2L plus or minus, that is the meaning of this symbol, 1 by 2 R by L square minus 4 by LC. Now, we will have real distinct solutions if R by L square is more than 4 by LC. Okay. This also can be written as this can be rewritten in a couple of ways. I could say 1 by R square root of L by C is less than half, or I could also write it as R by 2 square root of C by L greater than 1. Okay. These are some quantities that we will define later. Okay. So, then there will be two real and distinct solutions, which are minus R by 2L minus half square root R by L square minus 4 by LC, and the other one will be minus R by 2L plus half square root R by L square minus 4 by LC. Okay. Now, there will be two identical solutions. When I say two identical solutions, you will calculate P1 from this plus sign, P2 from this minus sign. Those two values will be the same as each other if R by L square equals 4 by LC. In that case, P1 and P2 will be equal to minus R by 2L. Okay. And there will be complex conjugate solutions. Okay. If R by L square is less than 4 by LC. Remember, in that case, this number inside the square root will be negative, and the square root of a negative number is an imaginary number. Okay. There is a comment here, I guess it is not a question. It says second order nonlinear equation can solve by Laplace transformation. First of all, this is not a nonlinear equation, this is a linear differential equation, and it is only a linear differential equation that can be solved by Laplace transform. Now, we have not even come to Laplace transforms, and we will not do that in this course. So, we will solve the transient response using time domain techniques. It is because it has two roots, there are many possibilities, but it is quite simple to do that in the time domain also. And in fact, understanding this is a prerequisite to a good understanding of Laplace transforms. Okay. So, now under these conditions, what happens is that I have to calculate square root of R by L square minus 4 by LC when this number is less than 0. What is that? What is square root of minus 1? Please answer this question. What is square root of minus 1? Yeah, it is denoted by the letter I or J, which by definition is square root of minus 1. Now, in electrical engineering, because we use I for current, we always use J for square root of minus 1. Okay. So, what is this? This is basically square root of minus 1 times 4 by LC minus R by L squared, okay, which is basically J square root of 4 by LC minus R by L square. So, in this last case, when R by L square is smaller than 4 by LC, okay, the two roots will be P1 is going to be minus R by 2L plus J square root of 4 by LC minus R by L square times 1 by 2, and P2 will be minus R by 2L minus J square root of 4 by LC minus R by L squared. Okay. So, we will have two roots which are complex, and not only are they complex, you see that they have the same real parts minus R by 2L and imaginary parts with opposite signs, plus half times this, minus half times that. So, these are complex conjugate pair roots. Okay. So, in general, a second order system will have three possibilities. It will always have two characteristic frequencies. The two characteristic frequencies will be identical if R by L whole square equals 4 by LC. Okay. This is for a series RLC circuit, and if R by L whole square is more than 4 by LC, it will have two real roots P1 and P2 which are different from each other, and if R by L whole square is less than 4 by LC, it will have a complex conjugate pair of roots. Is this part clear? So, we have to calculate P1 and P2 which are characteristic frequencies from the characteristic equation. Then what do we do with it? The solution can be exponential of P1t or exponential of P2t. Both these are possible. Okay. Okay. Now, it turns out that in a linear system, when you have a linear differential equation, when there are two possible equations, the general solution is a linear combination of the two equations. Okay. So, finally, let me write down the natural response. Okay. The natural response will be of the form a1 exponential p1t plus a2 exponential p2t, where p1 and 2 are characteristic frequencies. Okay. Or basically they are the roots of the characteristic equation. Okay. And what is the characteristic equation? All I have to do is to substitute p square where I have second derivative, and p where I have first derivative, and 1 where I have only Vc equals 0. Okay. This is exactly what you will get if you substitute Vc by exponential of p times t. Okay. And now we have to find out a1 and a2 from initial conditions. Okay. Just to show what I mean, I will go back to the first order circuit and do it that way. Okay. Let us say Vs goes from 0 to Vp, and we have RC, and I know that the steady state solution to Vc is steady state response equals Vp, and the natural response is some constant A times exponential Pt, where P equals minus 1 by Rc. How did I get this? I get this from the characteristic equation Rc times P plus 1 equals 0. So, the total response is the steady state response Vp plus transient or natural response A exponential P times t. Okay. There is a question which asks whether the characteristic frequency says something about the damping of the signal. Now, we will talk about that later. We did not introduce the term damping factor. Okay. Now, it turns out that if the characteristic frequencies are both real and negative, you will have an overdamped system. If they are identical, it is a critically damped system, and otherwise it is an underdamped system. But we will come to that in the next lecture. Okay. Coming back to the first order system, the total response is the steady state response plus transient response. But we have this constant A that has to be determined. How do we do that? That we do by looking at the initial condition. Okay. If you look at this total response and substitute t equal to 0 or 0 plus, okay, what do we get? What is the value of this at t equal to 0 plus? Just all you have to do is a mathematical substitution. So, the question is, the total response is of the form Vp plus A times exponential p times t. What is the value of this at t equal to 0? All you have to do is to substitute t equal to 0 in this, and if you do that, you will get Vp plus A. Okay. So, if you have Vp plus A at t equal to 0, so Vc of 0 happens to be Vp plus A. Okay. So, obviously then A has to be equal to A has to be equal to Vc of 0 minus Vp. Okay. And I can go back and substitute this into the equation. So, I will get the total response to be Vp plus Vc of 0 minus Vp exponential p times t, which is minus t by Rc. Okay. And this is exactly what we had obtained earlier using a different technique by completely solving the differential equation. Okay. But the advantage of this method is that it can be extended to second order circuits as well. Okay. So, in general, the way to solve it is as follows. Okay. When we have constant or step inputs, you first determine the steady state solution. Okay, and this you do by open circuit the capacitors and short circuit the inductors. Then you determine the natural or the characteristic frequencies. For a second order system, you will have two of them, P1 and P2. So, then this means that the natural response will be of the form A1 exponential P1t plus A2 exponential P2t. Okay. And finally, the total response will be steady state plus natural response, and you will have to determine these two constants A1 and A2, which you do based on initial conditions. Okay. So, this I showed for a first order system. Exactly the same thing is true for a second order system. Okay. Is this clear? Any questions? Any questions about this? In a second order circuit, we will have a second order differential equation and two characteristic frequencies. Okay. I see some question, but it seems to be half typed. I am not able to understand what the question is. Okay. In case of first order, there is only one characteristic frequency, and it does not matter what the values are. Okay. The characteristic frequency is always going to be negative. It is minus 1 by RC. Okay. For a passive first order RC circuit. For an RL circuit, it will be minus R by L. Okay. So, there are in case of second order, there are three distinct classes of solutions, because there are three possibilities for the characteristic frequencies. In case of first order, there is no such thing. There is just one case, and it will always be an exponential. Okay. Okay. So, in the next lecture, what we will do is we will start from this point and see what these solutions look like, and that will also take us to these different kinds of responses, which are under damped, critically damped, and over damped. Okay. I will not go through every detail of this, but what I want to point out is, for a second order system also, you should be able to write down the natural response and even the complete response in case of a constant input, that is a step input, okay, by evaluating the initial conditions correctly. Okay. So, now if there are no more questions, we will stop here and continue next week.